So we're going to cover the geometric distribution today. That'll be about half of class. And then the second half of class, since we've got a little bit of breathing room, I think I'm going to go back over sort of some aspect of the general analytic approach, and we'll just think of new problems and kind of solve them. Come up with a phenomenon, model it, and use Python to sift through the results and answer questions. So today we're going to be talking about the geometric distribution. And, right, this is geometric. So the geometric distribution has underneath it Bernoulli trials, much like the binomial distribution. And we were able to extrapolate Poisson from binomial, but we're going to think of geometric not from binomial so much as just from Bernoulli trials. So remember, a Bernoulli trial is just, let's think about it as a heads or a tails, right? These are the two possibilities, heads or tails. Geometric is a series of Bernoulli trials, like binomial. However, it's a series of failures before the first success, okay? So before the first success. That's what we're modeling. And the way that we can think about that is, if we're thinking coin flips, why not think about this in terms of coin flips? It's convenient. That's going to look like, tails, 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 heads. Okay. Tails, heads, right? These are all samples. Here's the first sample, second sample. And let's say we have a third sample that just starts at heads. And we could keep going like this. So something to notice is that the number of trials varies, right? So we need to think about this as the number of trials. And that's really the thing that we're focusing on. So if we have a probability, let's say we have a probability of 0.5 in this case. If we have a probability of 0.5, we might ask the question, what is the probability that there will be k trials before the first success? Okay. So even though we have this Bernoulli process under the hood, just like binomial has a fixed number of trials, right? Geometric has a varying number of trials, and in fact, we're focused on the number of trials it will take to get the first success. Interesting thing about this, there are two ways that we can consider the probability mass function. Okay, so when we're thinking about the geometric PMF, there are two ways that we can consider this, right? We can consider up to and including the first success, right? So that would be something like tails, 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 heads, which would be 5 trials. Or we can consider tails, 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 heads, and only think about the 4 trials before we get success, okay? And this is where this can become a point of confusion with the geometric PMF because there's 2 different forms of the PMF. So let's just look at those 2 forms. They're very similar. Just one accounts for inclusion of the PMF and the other does not. So the probability that X is K, and again, K here just means the number of trials up until the first success. So, 4 trials, let's say, what is the probability of 4 trials up to and including the first success? Well, that would be the probability of success multiplied by the complement of the probability of success exponentiated to the number of trials minus 1. So I call this inclusive. That's how I think about it. This is an inclusive PMF. It's inclusive of the success. And then we have an exclusive PMF, which will be slightly different. So the probability x is k. This is just the probability multiplied by 1 by the complement of the probability raised to the k. All right? So either one of these will work to answer the same question, and that's the important thing to realize, but it does affect how you think about the question, okay? So let's see if I have an example. Let's see. Yeah, let's think about an example, because I think that will be helpful at this point. I don't actually have one on hand, but I can just make one up. All right, so let's imagine this scenario. You're sitting on a park bench. There is a how about 0.2 probability that any given person walking by is wearing a red hat. What is the probability that the first person you see wearing a red hat is the fourth person who walks by? Okay. So we know our probability here, right? We can see our probability clearly. The probability of wearing a red hat is 0.2. So how do we think about k? All right, so k, if it's inclusive, our first success is the fourth person, right? So k inclusive would be 4. K exclusive would be 3. Okay? That's all. That's it. You can use either formula. It doesn't really matter. It's how you interpret the question. That's what matters. So with that in mind, you know, I used to teach this material and say, okay, we're going to code both functions. One is going to be inclusive, the other is going to be exclusive, and we're going to write a lot of code around that. I think ultimately that just ends up being a little confusing. I think the better thing for us to do is to consider this from the point of view of you're going to choose one formula and probably use that one primarily. You know, you're not going to use one in one situation and the other in another situation necessarily. That's not really going to be the case. You're going to choose one. There just happens to be two that are equivalent. Okay, so there's some conveniences with the geometric distribution. Some nice conveniences. So these formulas are very simple. They're very straightforward. We even have a closed CDF that you'll see instead of having to run a summation over the PMF, although, of course, you could run a summation over the PMF. That would be fine. The formula for the expectation of our random variable is just 1 over the probability. Okay? That's really straightforward, right? So how many, if it's 0.2, how many trials would we expect? Well, if it's 0.2, how many trials would we expect? It would be 1 over p, 1 over 0.2, that's 5. So that should be a fairly simple, fairly intuitive thing, right? We're most likely to see a red hat on the 5th person walking by, you know. Okay, so the That's up to and including the first success. Now, right, that's inclusive. So this is where we have to be careful. If we're talking exclusive, it's not more complicated, really. It's just, 1 minus p over p. And so we'll end up with the same answer, right? Exclusive, in this case, we would say 1 minus 0.2, which would be 0.8, over 0.2. So our expectation would be 4, right, in that case. And that would be 4 occurring before the first success. It's the same answer, right? There's nothing different about those two approaches. So I think what we'll do is we'll go with the inclusive forms, and because I think they're somewhat more intuitive for a lot of problems, although I think in some cases the exclusive form feels more immediate. I don't know. But we'll just use the inclusive forms. There are some other conveniences. Some very straightforward, simple kinds of ways to look at the different moments of our distribution. The variance of x is going to be 1 minus p over p squared. Pretty straightforward. Turns out that the variance, the exclusive variance is the same formula. But, the inclusive and exclusive have the same formula here. So I'm going to have you code the geometric PMF. This should be pretty straightforward. We're going to take the inclusive form of it, as I said, and we'll use that to answer this question. And let's do 4 minutes on this. I think I was thinking we could do 3, but let's do 4. Oops. All right, so code the geometric PMF function. 2 parameters, probability, k, which is the number of failures, inclusive or exclusive of the first success. We're just going to consider inclusive. So I'll just cross that out. And don't worry about this inclusive is true. Let's just code it simply with a p and a k. And, that'll be it. Cool. So I'll set a timer for 4 minutes. Go ahead and code that up. Okay, yeah, so this is pretty straightforward, right? I'll go ahead and code this up. It's a single line. Here, I'll just do this. Single line function, right? It's geometric Pmf, geometric Pmf, and p, k, and we're assuming that we're going to be inclusive on it. So this is just going to return the probability multiplied by the complement of the probability raised to 1 less than the number of trials. So it's just that. And if we want to know the, what is the probability that we see our first red hat on the fourth person, let's find out what that is. All right. So looks like that's right around 10%. Does it matter what order the parameters are in? No, it doesn't. As long as you know, right? That's what really matters. As long as you're aware of it. I tend to put I tend to put probability last because I'll often use a default value for the probability, but that doesn't mean you have to do that. If you remember yesterday or the day before, I think it was yesterday actually. Not yesterday, Thursday. On Thursday, I had the binomial Pmf, and I actually switched the parameters into the binomial Cdf. And that may have been a little bit confusing, but that's something you can do. It doesn't really matter as long as you can trace that in your code. Although it is better to align kind of with consistency when you do this sort of thing. So I'm going to do P and K here. I'm not going to do K and P, in the binomial CDF, like I did with the binomial PMF. In fact, I should go back and repair that in my prior code. It's not wrong, but it can be confusing for people. Okay, so let's answer a question with this. Another question: what's the probability that you get your first? If you're flipping a fair coin, what's the probability you get your first heads on the 7th flip? And offhand, you might think of this as being pretty unlikely, right? But we don't really know how unlikely this is going to be. So here, I'll grab this. So you're flipping a fair coin. What is the probability that you get your first heads on the 7th flip? Our probability is 0.5. It's a fair coin. And we're talking about the 7th flip. The first heads, that's inclusive of the 7th flip. So we should be able to just call this function and see a result. So that's a tiny probability, right? 0.7. That means that, roughly 10 out of 1,000 times you're going to of performing this operation, you're going to get your first heads on the 7th flip. That's something you could verify in the real world, right? You could sit there with a coin and, do this and, use a sampling process to discover this. At any rate, it's very small. So let's think about maybe a more realistic scenario, since we're not going to be sitting around flipping coins all the time. Let's say you have a series of routers transmitting packets of data. There is a 0.99 probability that a given packet of data passes through a given router. What is the probability that a given packet of data is lost in the 15th router? Okay, so what do I mean by this? If we think about a network of routers, and this is an applicable place, like a real world place where we might think about the geometric distribution. And let's say all these routers are the same brand, and maybe, they split off in these ways, and they sometimes come back together. It doesn't really matter. We're not going to necessarily calculate these things, but at the end of the day, these are going to lead to the same destination, right? So here's our source, here's our destination, and for every one of these, when the packet hits this router, there's a 0.99 probability that it will pass through. Okay, and so if we're asking the question, what is the probability that a given packet of data is lost in the 15th router? Is this our probability of losing data or the data being successfully passed? Right? And this, obviously, this is a measure of success. But we have to reconsider what we mean by success. If we're asking the question, the probability that a given packet of data is lost, then we have to think of success as being defined as a packet lost. So it's actually going to be the complement of this in regards to losing a packet. So our probability here is going to be 0.01. It's going to be the complement of the probability of the packet going through successfully. And then, the other part of this is very simple. The packet of data being lost in the 15th router, right? Like maybe the router has too many packets, it overflows its packets, and it, drops the extras, which is something routers do. So, how do we answer this? It's pretty straightforward. We can kind of take these same way that I put this here. We'll just change these values. We'll change the probability, and we'll change the inclusive value of k. And I'll just put the question here in case you're referencing this code later. Also, all this code, of course, is in the slides. Okay, so 0.01, and we're talking about losing the packet in the 15th router, so this is just 15. So, 8 out of 1,000, roughly 9 out of 1,000 chance that we're going to lose our packet in the 15th router. But the thing you have to wonder, is this a helpful question, right? Why might this question be helpful? Well, if we think about it in the context of we're noticing packets being lost at a certain frequency in a certain router, and we have this overall sense of the probability of packet loss in a given router, especially, let's say on, at the 15th position. If we can answer this question and we see that packet loss in reality is much higher than this, then we might think there's something wrong with the router, right? Like, and when you're thinking about these types of these distributions, it's good to kind of consider the real world, right? It's good to bring it into the real world. It's really, and you need to really understand it. Whether bringing into the real world means inventing questions that look like this, the probability of somebody who walks into your store buying, a specific, coffee drink or something. You can write these stories, and you should. You should write a few of these problems because that will concretize what these are. That said, that's writing a problem, but thinking about how this actually is contextualized in the real world and where you might apply it is the next level of writing the problem. So all that said, we're generally not, in the real world, we're probably not as interested in the probability of losing a packet at a specific router in most cases, unless we're trying to diagnose the router. What we're likely more interested in is the probability of losing a packet somewhere up to and including this router that we're considering. And so that's a different question, right? that's a question that requires the Geometric Cdf. And it turns out that there's a very nice closed formula for the Geometric Cdf. And that is the probability that x is less than or equal to k is 1 minus 1 minus p to the k. That's the inclusive form. I'm not going to bother writing the exclusive form down, since we're focusing on the inclusive form. But if you want to see both forms, definitely they're all in the slides. So 1 minus 1 minus p to the k. Very simple closed formula. So you're going to code the Geometric Cdf. And there are two different ways you could code this, right? You could code this from the PMF, which I should have shared, but I didn't. Let me just share that really quick. So you can code this by traversing all values from 0 up until... wait, all values from 0? I always have to think about this. Yeah. Yeah, this becomes a language issue. I have to think about this. Up to and including the first success, can you have... You can have 0. I'm sorry. The other form of the formula, you can't actually have 0. So that's, something I'll talk about in a little bit. But you're going to code the Geometric Cdf. And let me just give you a little starter code down here. And I'll paste this in. So def Geometric Cdf. And this will be the inclusive form. And you need probability and k high, right? And let's just do 2 minutes on this. I think it should be pretty straightforward given the formula. Yeah. Okay. So I'll put 2 minutes and just try to code that up really fast. Okay, so this will be pretty straightforward, right? I'll just grab this. And once we have this, we can use it to answer maybe questions that will come up more often, right? We're often thinking about, the bounds of trials where we'll get a success. Not necessarily will we get success immediately on, only on the 127th time this happens. Okay, so this is just return 1 minus 1 minus p to the k. That's it. So we can use this to answer... Shoot, 1 second, sorry. There we go. We can use this to answer fairly straightforward questions, right? And here is sort of an adaptation of that prior question where we have a series of routers transmitting packets of data. There's a 0.99 probability that a given packet of data passes through the router. What is the probability that a given packet of data will pass successfully through 14 routers, right? So we're going to have success through 14. And we can answer that very simply with this formula, with this function. We can print where the probability is 0.01 and k high is just 14, right? So we passed successfully through 14. Through 14. Oh, I'm sorry. Passing. Let me think about this. There we go. So if we're talking about it in terms of success and not being dropped, then that would be the case. So this will be successfully passing through 14 routers. And let's see what that is. Oh, K is not defined because I called it K high. Okay. So that's pretty probable, right? Like, we're probably going to pass through that many routers. And to me, that looks like rounding error. Like if we decrease this, if there's a 50% chance of passing through a given router. So, sorry, I think this is the thing about the geometric problems. I don't know, they often kind of confuse me a little bit. And I think I am a little confused on this problem. Sorry about that. Okay, so let's break this down. Successfully passing through 14 routers. Probably being dropped. Let's see. Let's answer the other question, because I do think this is correct. I don't know why I'm... why don't we take the sum of k? We have a closed formula in this case. We could take the sum of k. That's something we could totally do. But, and the way that would look is, well, I'll write that function in just a second. How about that? But, sorry, I'm trying to disambiguate this question for myself. I often do this specifically with geometric questions. And I'm not sure exactly what it is. So that gets me hung up on them. What's the probability that a given packet will be dropped before the 15th router it passes through? So dropped on or before the 14th router. So this will be, how about we call this dropped before 15th. So 14 is still our k high. It's going to be dropped before or on that. And this is going to be 0.01. So let's make sure that these are correct. Yeah, there's something amiss here. Is there something wrong with my function? That's the first question. So 1 minus p to the k. Range 0 to k plus 1. Yeah, let's look at this. This is interesting. I don't know why I'm getting hung up on this, but so I'm going to grab that accumulator form of this and return. Make sure I return the CDF. Okay. So successfully passing through 14 routers. 0.99, 14. That makes sense to me. And then let's just see. Okay, so we're getting the same. Oh, I'm sorry, I'm calling the wrong function here. How about let's copy this line. Oh, okay. I know what's going on here. I am misthinking this, and I'll show this in just a second. Falling for like a common sort of error. All right, so those two values are the same. Geometric Cdf through the closed formula and through the accumulator are the same. We're seeing a slightly different value out here, 0.13125 versus 0.13162. that's going to be rounding error on the computer, right? We're accumulating some values that let's just say don't have meaning. They might have meaning in the PMF, but when you start summing all of them, we get some, in this case, we get some extra value, right? And that's an important reason to round things in probability, because the significance of what ends up out here in the wings diminishes and diminishes. So that's just something to keep in mind. Okay, so drop before the 15th. Successfully passing through 14 routers. Okay. The reason why I tricked myself in this, I wrote, it's like I wrote all of this. This is just 0.99 to the 14th power, right? This is not a question we want to answer with the geometric PMF, even though we could, but we don't want to. What we want to do is answer it simply by saying this is a series of events, and according to the multiplication rule, it's just 0.99 times 0.99 times 0.99 times 0.99, 14 times. And so what we get out of that is going to be this value, something like 86.9% probability or chance that it's going to pass through 14 routers. So if we think about this, just to clarify, this is a 1, a 1, a 1, a 1, right? If we're thinking 0 and 1, failure, success. This 14 times. That might be 14, probably not. Add a couple more ones, but the reason we can do that, if we think about successfully passing through 14 routers, that's just 99 squared. Through 3 routers, it's 99 cubed, and that's what happens when you think you're being tricky, and then you trick yourself. Okay. All right. So, given this, we can answer better questions than, than how do I say? When we're thinking about the geometric distribution, we can start answering questions that look like the real world. And, we've been able to do that with binomial to some degree, with coin flips or, observations of some number of trials, like signals in a circuit. With Poisson, we're able to do that with people going into a store or geese walking by or whatever it might be. We could use stars in the sky in the Poisson distribution, actually. That's like a really interesting celestial phenomenon that follows a Poisson distribution. The number of stars in a given area of an image will follow a Poisson distribution if you keep sampling images. And here with the geometric distribution, we can think about how many times it's going to take to get a success, right? These are practical. They're not just abstract, and I want you to think of them in a practical light as best you can. Try to think of things in your world where you have a known probability, and you're trying to consider, well, how many times, if there's a probability rating on the tire for your car in terms of it getting a flat, right? Like, we could look that up. We could say, okay, well, what's the probability of getting a flat just on this mass average of cars? It's not going to be accurate to your car necessarily, but you could try to start answering a question like, what's the probability that the 7th time I take my car out, I'm going to get a flat? It's probably extremely low, but it's something that you can start to answer. And it's important to start thinking of your world in that light. Like, what kinds of questions can I start answering? Can I approach answering? That's probably a better way to think about it. What kinds of answers can I approach answering? Or questions can I approach answering? Okay, so in the tradition of coding PMF dictionaries, which we've been doing a lot of, I've got a breakout here. And I'll give you 5 minutes on this. So I'll give you a little bit of starter code. This is going to be the Geometric Pmf dictionary. Okay, we've got a probability of success. We've got k high. So what this should return is a dictionary where the keys are values of k, and the values are, of course, probabilities of it taking that number of trials to get a success. Okay? So I'll put this in the Slack. And I'll put 5 minutes on a timer. And yeah, see if you can code that up. This is like the archetypal kind of thing that we're going to ask you to code up. Okay, so I'll code through this just step by step. This, like I said, this is kind of an archetypal thing that you'll need to be able to code. We're using a dictionary, which I'll instantiate. And then we want to go from the lowest value of k, which is going to be 0 in this case, okay? And let's see. For k in range, and we'll say k high plus 1, okay? And then we'll say d sub k is going to get the geometric Pmf, p, k, and inclusive. Oh, I'm sorry. We need to go from 1 in this case. That's kind of a tricky thing. So let's think about that just in terms of semantics. If we're talking about failures before the first success, right? If we're talking exclusive, and I should really be clear about this, failures before first success, then what if we get success on the first trial? Then we can have 0 failures, right? So we can have 0 failures before the first success. If we're talking inclusive, then what we're really talking about is the first instance could be success on the first trial, okay? So that's subtle, and it's a semantic difference, and it is important. So we need to, essentially we should not include 0, and that was my mistake in the CDF up here. In this case, in this accumulator pattern, although we should still get rounding error between these two, I think the rounding error will actually be a lot less if we start our CDF at 1. So this means that success on the first trial for the CDF. Sorry about any confusion around that. It's like I have to think about it, you know, and I do this all the time. So, you know, apologies if that's confusing at all. Again, we're not using the exclusive form, we're just using the inclusive form. Okay. All right, so once we do that, we can just return the dictionary, right? We can just return that, and that should be a working function. So let's test that out. And I'll get a dictionary out of it, and let's think about this in terms of flipping coins. 0.5, and let's say we have a k high of 10. And there should be a fairly familiar pattern here that we see, okay? And let's just make sure. So for key value in d.items, this is a good form to know as well, you know, printing out the output of a dictionary, where this is k, oops, and that is v. So let's run that and see what we get. Inclusive is not defined. Oh, that makes sense, because we're not doing inclusive exclusive. Okay. All right, so let's interpret this, and let's interpret it in a couple ways. The probability of getting heads on the first flip is 0.5, right? That makes sense. That makes sense. That's just, it's either heads or tails, 0.5 probability. Probability of heads on the second flip is 0.25. And, why is that? Why would that be 0.25? Well, let's think about this in terms of different possibilities. If there are two flips, we can get tails, 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 heads, heads, tails, and heads, heads. Only one of these satisfies that criteria, and that's 1 out of 4 of the possibilities, 0.25, right? And we can take that a step further in this third trial. Okay, well, probability of getting your first heads on the third trial, that's 0.125. All right, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. How many of these, right? How many of these fit the criteria that we're explaining here? So it's just this, 0, 0, 1, right? Tails, tails, heads. That's the only one that satisfies that. That's 1 out of 8, or 0.125. And what you might notice here is this is what we might call a geometric series, where this is just 0.5 raised to the, well, essentially the n, where if n is 1, it's 0.5. If n is 2, it's 0.25. If n is 3, it's 0.125, and so on. So we are just exponentiating this according to the specific trial. Okay? And this is a geometric series with 0.5 as our constant. If we change this to 0.3, or let's say let's do 0.25 just to drive this idea home. We're going to say this is now 0.25 to the first power, 0.25 to the second power, 0.25 to the third power, and so on. So hopefully that makes sense. What we're seeing here. This is a very important pattern. Oh, can I show code again? Yeah, I think so. I modified your function, and I think there's a chance that notice the range. The range here, I'm starting at 1. Did you change that? If you change that, I think you should get the same results. So let me paste this whole thing in, just in case there's some other something else going on. So yeah, try that out, and if you're still having an issue in that code, we can track it down after the break. So, in fact, why don't we go ahead and take a break? I'm going to leave this up here. This what I like to think about this as geometric decay for a very specific reason, but it's just a geometric series. We can, if we perform the CDF and use these same arguments, 0.5 and k high of 10, just think about how the CDF will display. So we'll code up a geometric CDF dictionary afterward, and after if there's still issues with your code, we can troubleshoot that and then code the geometric CDF. Yeah, just think about that. How would this output differ if this was the CDF? Just think about that. Okay, so let's, let's continue forward with this idea. So I had you code the Geometric Pmf dictionary, and now I'm going to have you code the Geometric Cdf dictionary. So should be pretty straightforward. And we'll do 4 minutes for this. Actually, let's do 3 minutes. And there's a reason for that, which I'll show you. But you should be able to build... Oh, I'm sorry, that says PMF, doesn't it? Let me just delete that and fix it. Let's do Geometric Cdf. Basically, you should be able to adapt your prior code. So we'll just do 3 minutes on this.
Ready for the conversation about the fact that everything they complain about with men mansplaining is exactly what they do to women of color all the time?
Okay, so all we need for this Geometric Cdf dictionary, we can grab right here. So I'm just gonna snag all of this actually, and put it here. And the only thing that's gonna change is passing in this geom CDF. That's all that's gonna need. So if I run this, let me make sure I have everything. Need to uncomment all of this, and we'll go here, CDF, and I think that should work. Okay. All right, so let's just put the CDF and the PMF side by side. All right, so this should be really obvious, what's going on here. 0.5, it's going to be the same for the first trial. And then if we take 0.5 and add 0.25 to it, we get 0.75. If we add 0.125 to that, we get 0.875, and add 0.0625, etc. Notice that as our CDFs do in discrete distributions, they will tend toward 1 as we go further to the right. And you might wonder, well, will this ever get to 1? Will it ever get to 1? Well, why don't we call this with 10,000? And, well, it looks like we get to 1, but in reality we didn't. This is just a rounding error. So maybe if I do 1,000 on this. And this is an important thing to consider with computers. It's not a certainty that we get to 1. We should never be able to get to 1 in this pattern. It's just we can't store something precise enough, so at some point we get 0.999999 far enough that our computer's like, I give up. I'm just going to make this 1. So, I just want to point that out, right? And you can see that right here. 858, 929, 964, 982, 991, right? We get to past 53, and our computer gives up. So keep that in mind. There's a reason under the hood that we cannot, we need to get to infinity, right? Which is not a number per se, but it's a construct of an idea of number. We get to infinity, and then we have certainty. But, of course, we can never get to infinity. So just be careful how you interpret this idea that we're seeing in the CDF dictionary. Okay. So that was a lot of closed formula. But you know, we have other ways of thinking about these kinds of problems. Oh. Is K referencing the K in range? Is K referencing the K in range? So for K in range, 1 to K high plus 1, K is going to take 1, and then 2, and then 3, and then 4, and then 5, and so on. So we're getting, you know, we're just getting the associated probabilities for each of the counts of K, right? So 1, 2, 3, 4, and so on. Is that addressing your question? I may not be understanding your question correctly. The K that is passed in is the parameter. Yes. Yes. So both the K that is passed in as the key right here and the K that is passed in as the argument here are taken from this K in range. Those aren't coming from anywhere else. Does that answer your question? Okay, cool. Awesome. Yeah, that can be pretty confusing, especially since a lot of what we've been doing at times is not necessarily using this value. And if we sample, let's say if we sample K, sorry, if we're sampling, then this would be like an underscore, and we'd be doing some other operation within here, right? This would be an underscore, and it would be disposable. But in the closed formula, often we are using directly the iterant, right? The value that holds what the iterator is passing to us. The iterator in this case being the object from range. Okay, so let's think about geometric sampling. Geometric through a sampling approach, and we can borrow from before. We can borrow this Bernoulli function that we've already seen a couple times, right? Where we say if random, right? We get a random number between 0 and 1. If that's less than the probability, then we return true, or in this case, we'll return 1. Otherwise, we return 0, okay? Of course, I need to say from random, import random. So that should be pretty clear. So if we're thinking of a way to sample here, we could write a function that will sample however many times. We'll put an upper bound on the sample, and it's going to be a slightly different function than we've seen in terms of sampling. Let me say that, and then I'll just start coding it. So we have this geometric where we have a probability of 0.5, okay, by default. And we're trying to, well, let's make a collector. Let's do this. Let's make a collector, and we'll collect in the results of sampling Bernoulli. And I'm going to say for whatever in range, this is our sampling construct, right? We're going to do this some number of times. But notice I don't have a num samples parameter here, and there's a reason for that. Instead, I'm going to sample this many times. Why not? I'm not sure. That number might actually be too big to pass into range, but we'll find out. I'm going to get, say, a flip or the result of a trial of a Bernoulli trial on P. And then I'll append that. So I'll append the flip. Okay. If that flip is 1, then we break. So notice that if we're breaking, if the flip gets to 1, we're probably never going to get this many samples. So let's just return that list first and see what this gives us. Right, and the reason we're doing sampling here is just to observe the phenomenon. I think it's a good idea to do this kind of thing. Okay, so we got 1 on the first flip. And that time we got 1, 2, 3, 4, 5, 6, 7. 7 flips if we're being inclusive of the first success. Then we got it on the first flip, second flip, first flip, right? So maybe this would be a little bit nicer to look at if we said this was 0.1, probability 0.1 for success of any given trial. And now notice we're getting a lot more trials inclusive of the first flip. Okay, so if we're trying to gather our K, right? K is the thing of interest here. If we're trying to gather K, how many trials up to and including the first success, we actually don't want to return the list itself. We want to return the length of the list. If we were being exclusive, we would return the length of the list minus 1. Okay? So let's just return the length of the list. And I'll run this again just so that you're clear about what we're returning. We're returning how many trials it took to get a 1. 1, 16, 1, 21, 1, 12, 33, 19, 8, so on and so on. Okay. So we're kind of taking a different lens on the same phenomenon. We can analyze this. So how do we analyze it? We pack the results into a dictionary. That is the thing that we generally have been doing in our analytic approach. So let's say geometric samples dictionary. I'm going to set the probability to 0.05. Why not? By default. And let's say that we're going to sample 10,000 times. So if you're thinking about this, what we're going to do 10,000 times is we're going to call out to geometric. We're going to call out to that 10,000 times, and we're going to get these integers back. We're going to check to see if that integer exists in a dictionary, and we're going to increase the counts of the occurrence of that integer being returned from geometric. Okay, so how do we do that? We code a dictionary. We pack in a dictionary. And so I'm going to say for whatever in range, the number of samples. This time we do have a fixed number of samples because we're sort of looking at a different level of the phenomenon. Now we are sampling the phenomenon, whereas in this case we were sampling in order to model the phenomenon itself, right? So this is an illustration of the phenomenon. This is calling out to that phenomenon to look at the outputs of it, the outcomes from it. So I'm going to say the number of trials. This is going to get geometric of P. We just pass the probability into that. And I can say if that number of trials is not in the dictionary, then I can put it in there. I can say the number of trials is going to get 0. And in every case, we're going to increment this. So plus gets 1. And we can return the dictionary like so. Okay. So if we want to explore this idea, all we have to do is call this dictionary and look at the output. Okay. So D is going to get this, and I'll just use the default values. And I'm going to say for key value in the sorted version of this. Now, why am I sorting this? Does anybody remember why I need to sort this? Any thought on that? Yeah, to organize the data. Yeah. And in these sampling processes, we can't guarantee that this first call to geometric of P is going to be 1, right? And so the first thing we put in our dictionary may not have a number of trials 1. We're not going to get these in order. It's very unlikely that we would. So it's very unlikely that our dictionary would have the K values in order. Order in a dictionary, we say dictionaries don't guarantee order. That's not exactly true anymore. That used to be true. It's order in a dictionary is the when that value is put into the dictionary. It kind of has an order by the time it was added. So in that sense, we are not guaranteeing the order that would be convenient for us, and so we'll go ahead and traverse this in a sorted way instead. So again, this is that other recurring pattern that has an F string, and we pass in the key and the value. And if we print this out, my suspicion is this will be kind of long, right? So notice what we have here. We have everything from, well, the first value, which is the most probable, it seems, right? The most occurring. And I guess we're sampling this. How many times did we sample this? 10,000. Okay. So we're sampling this 10,000 times, so that makes sense. And down to these values out in the wing, right? Where we're going to start skipping. We're going to start skipping k values out here. And the further we get, the more we'll skip. So like 22, 24, 25, 28, 29. Although the skipping here is a little bit globby, to be honest. It's kind of interesting. How would we fill these in? Well, we'd take more samples probably. But if we take more samples, here's the issue. We're going to extend the wing, right? So why don't I do that just to demonstrate? If I run this 100,000 times, we're going to extend the wing somewhat. Interestingly, we didn't that time. Oh, no, we did. We did. Just by a little bit, though. That's not really a significant amount, but we do extend the wing, and so we're still going to get these globs kind of in between. And so what I would recommend, if you want to take this toward the theoretical distribution, is to sample your samples, right? Is to run many trials of your sampling process. So let me just give you this code if you want to play around with it. I think these kinds of things are very illustrative of the phenomena that we are looking at, right? You'll need to import random for that. So from random, I'll just edit it to say that actually. So from random, import random. Okay. So that should work as is. So how do we approach the theoretical distribution? Pretty simply, let me just write this up really fast. This is going to be very much like, well, it's basically the same process that we use with the binomial distribution. So I'll just demonstrate it. So geometric samples, I'll call this a probability dictionary. Should I do it like that? I'll do this. I'll do it like this. Geometric samples trials, and we'll code this up from there. So I've got this dictionary function. I'm going to borrow some code from it. Okay, so what do we have? We have number of samples, and then we're going to want to have number of sample trials. Okay. So number of samples and number of sample trials. And let's set that at, I don't know, let's set it at 100 just to be kind of fair, kind of nice. All right, so for whatever in range, number of samples. Okay, so this is going to be our sort of an internal loop. All right. Although we don't need all of this, right? We can just borrow this functionality directly. So I'll do this, geometric samples dictionary, and we'll pass in the probability and the number of samples from the argument above, and that will sort of do away with our necessity to have that. I'm going to make an output dictionary called dout. So dout is going to be an empty dictionary. And I'm going to say for key and value in, actually let's wrap this in a loop. So for whatever in range, the number of samples, right? Sorry, the number of sample trials. So this outer loop should perform 100 trials of, and then the inner loop is going to be, is going to sample 10,000 times from this. So for whatever in range number of sample trials, for whatever in range the number of, well, actually, let's just do this. So we get our dictionary, and our inner loop is just going to traverse this dictionary. So d.items, we can say if k is not in dout, right? Then dout sub k is going to get an empty list. And I like doing this like this because I want to return the averages. And then in all cases, we're going to append to this list. So we're going to append the value to this list. We do that 100 times. D itself is sampling num samples times, which is 10,000 by default. And the last thing that we'll do in here is we'll process dout. So for key value in dout, I'll just say dout is going to get, dout sub k is going to get the length, the sum of this list, right? This is a list. Maybe just to be more clear, I'll put list divided by the length of the list. That's going to give us averages. I'm going to round this. I'll round this to 3 places, I guess. No, let's round it to 5 places. And then we can traverse this and see what's happening here. Notice this is us getting to counts, right? We are getting the average of the counts through this sampling process, and this is how we will approach the theoretical distribution. But in its current form, just to be very clear, this is not the theoretical distribution. It is a sampling process. Okay. All right. So in d.items, print k and v, and I'm sure there's an error or two in there, but let's find out. So 100 trials of 10,000 samples is probably going to take a couple minutes. Oh, what's going on there? Okay, so for k list in dout can unpack non-iterable int object. Okay, we need to do something that may not be entirely obvious here. If there's only one item in the list, we're gonna have a little bit of trouble with it. So I think that's what's happening here. How about I print our list? Actually, let's do this. If the length of the list is 1, then dout sub k is going to get list sub 0, and we'll continue there. So let's see if that works. We'll find out. Okay, I think we're still getting an error here. Let me reduce the number of samples and we'll troubleshoot from there. Okay, so on line 134, for klist in dout, dot items. I am notorious for forgetting dot items. Either way, this if statement, this if statement right here is fine. I mean, we're going to sum the items in the list. We don't actually need it. I was thinking the error was different than I assumed. So we can see all these ones that aren't 1.0. It makes sense that they're not. But yeah, we'll leave that as it is. I think it's fine. So here are our expectations. And I think this is a good thing to see, right? This is what we expect, the count that we expect to see for all of these items. And given that our probability is 0.05, our count for any given item is pretty low. I think that's pretty interesting. However, you have to recall that we are only taking 100 samples. So let's change that to 1,000. Yeah, let's change it to 1,000. I think that'll get us reasonably get us some reasonable result. And we can see here that we're very clearly peaking at 1. So let's change that again to 10,000. And here's the thing about these approaches is if you're trying to trend toward the theoretical distribution when you do this, it's going to help to take more samples. It's going to help to do more trials. And that's just an important thing to consider if you model things in this approach. Okay, so that worked. We're a little less globby out on the end here, although there is some glob. I think we're not really going to be able to lose that unless we drop non-contiguous numbers, right? So 211 to 213, maybe we drop everything after 213, and we just keep everything less than 211. We could do that. There are ways that we could do that programmatically. So at this point, if I were to look at the actual probabilities of these, that would, well, let's just do that. I'm going to write this geometric probability, this is sampling, so samples probability dictionary, and we'll pass in these same values, right? And this is going to be similar, right, to what we just had. This time, I'm going to build this from, let's see, the geometric samples trials. Let's grab that little snippet. And let's see, I need to get rid of these values. Oops. And then we can define, a transformed version of this. So I'll just call it dout, that is. And that'll be a dictionary. And I'll say for key value in d.items. And all we have to do in this case, I need number of sample trials as well. Num sample trials, it's 100, is look at, well, just add to d sub out sub k, or d out sub k, the value, okay? And we should be able to divide that by the number of samples. Now, that gets a little weird. What might make more sense is to sum d dot values and round that. I think that's actually a little bit better, given what we're looking at. Okay, so this should get us a probability. Okay, so let's return d.out and likely find that there's some kind of error in here, but that's also okay. And for k, v in the sorted version of d.items, let's print k and v. And I'm gonna change this probability to 0.5 just to see how well we're doing, because we know what we should get with a PMF dictionary. So that'll take a little bit to run. And notice we're not getting perfect values, but we're getting pretty close. Now let's round these. Let's round these to 4 places. Let's do that. And take a look at it. I think that'll be a little bit better. A little clearer. Okay. So 0.5, 0.25, 0.125, right? 0.0625. This is a reasonable way to approximate the theoretical distribution. I think that's an important takeaway with any sampling approach. And of course, the thing to remember here is it's going to do better if you take more samples. That kind of goes without saying. It's going to do better if we take more trials of samples. And maybe I'll demonstrate that as well.